Hello everyone and welcome to my presentation. Let me start by saying just a few words about myself. My name is Mateusz Hens and I have been working for 5 years at Google. Last 2 years I spent as a senior software engineer in Cloud Composer team. Today I would like to share with you some information about the efforts that Cloud Composer team is involved in Airflow community. As you can see on the screen, they are connected to isolation between user code and Airflow code, which we see as a problem in existing Airflow architecture. Let's start, and before we get to the solutions, let's take a look at how Airflow is set up today. What you can see in this slide is a very simplified architecture of Airflow that is used in Cloud Composer and probably in many standalone Airflow installations. I focused only on the most important components to make the picture as clear as possible. Airflow itself runs 3 different types of components: scheduler, worker, and web server. Scheduler is responsible for parsing DAG files containing the user code, putting them into the database, but also it runs another process called scheduler job, which is responsible for scheduling the tasks for execution. So it checks all dependencies for a task like time, parent task state, and if they are all met, it sends the task for execution by putting them in the celery queue. Celery queue, which is actually not a part of Airflow code, but just external component, and it's just a broken between 2 components, as on the other side of it, we have Airflow workers. There may be many of them. In Cloud Composer 2, the number of workers is automatically scaled for you based on the number of incoming tasks. Each worker has some number of slots which controls how many tasks can be executed in a single worker in parallel. If you take, for example, 6, then single worker can take up to 6 tasks from the queue at the same time. If all workers are occupied and setting for maximum number of workers doesn't allow our autoscaler to scale up, then tasks are waiting in the celery queue for some free slots. Airflow uses database to store its internal state and task and DAG execution history. Components simply write and read data from it during their execution. Users are able to upload their code to DAG as DAG files using Cloud Storage Bucket. Components that needs these files for execution, like worker or scheduler, sync their local storage with the bucket content. And finally, we have web server or Airflow UI, which allows users to see and manage DAGs and tasks with a nice user interface. In our customer cases, we see that some patterns occur more often than others. So we notice actually some flaws in this architecture. First of all, as I said, all components has access to the database. It must be open and accessible by every single worker, scheduler, web server, process running in Airflow installation. Usually, it requires root access on the database. So the problem is, the code executed in scheduler on worker is a user code, which means user is able to run any SQL query on the database, including deleting tasks, even unrelated, locking the database rows, or even the whole table. Believe me or not, we got few cases from our customers where the whole database got locked by some not well-written DAG. Secondly, I mentioned that scheduler has 2 processes. One for parsing DAGs, second for responsible for task scheduling. In Airflow 1, they were coupled more tightly. However, thanks to great work of community for Airflow 2, these 2 processes can be split and run independently. Some of customers encounters the problem when with many DAGs, the DAG processing process of Airflow scheduler starts the scheduler job. As the result, tasks are not scheduled or scheduled with a delay. Thirdly, long-running worker with a dedicated number of slots is nice from performance perspective. Usually there are some free slots ready to pick up the task as soon as it appears in the queue. But it also means there is no isolation between them. Tasks from different DAGs are executed on the same host, without any sandboxing, and they share the same resources. You can imagine the problems like one task failing with out of memory, and it crashes all the other tasks that were just unlucky to be scheduled on the same worker. Another problems are PyPy dependencies. Two tasks may require some external dependencies, which may conflict in many ways. Finally, user Python code provided as DAG file is fetched and executed on workers and schedulers. As it is Python, then everything is dynamic. Means the code is able to even change the Airflow code, install dependencies on the fly, and of course leaving this mess afterwards. It also has another problem. All code is stored in a single location, which makes it hard to, for example, share the instance even between different team members, for example, for development purposes. So just to summarize the problems, there is a direct access to the database for all the components. There are components running both user code and Airflow code with the same privileges. There are different tasks executed on the same worker. Actually, the same applies to DAG processing. And there is a single location for all DAG files. So yeah, Airflow has its problems, but of course, each challenge is an opportunity. Before we move to the solutions, I would like to briefly describe the high-level idea. We found that we can split components into two groups, trusted and untrusted. Components should be considered trusted if and only if executes Airflow community code. This code is checked during the code review process, also tested during the release preparation, and in Google we can run it through our security review before we add it to Cloud Composer for our customers. It also means no custom PyPy dependencies or plugins, just to make sure the code that is executed here is fully auditable, which of course excludes even accessing the DAG files in any way. And due to that fact, we can audit the code, so we are sure what kind of DB access or what kind of DB queries are executed here. So trusted components may keep the direct connection to the Airflow database. On the other hand, we have untrusted components. They execute the user code either from DAGs, plugins, or PyPy dependencies. However, due to that fact, the access to the database should be limited and possible only through some API. When we approached community about these problems and ideas, we quickly learned that they share the same concerns. We decided to work on fixing this issue in Airflow community and merge all our changes there, so not only our customers can benefit from them, and we can still keep 100% compatibility with Airflow in Cloud Composer. We learned that the ideas that we had fit well into the Airflow multi-tenancy effort run by the community. So far, we prepared two AIPs, Airflow Improvement Proposals, that you will learn about in a minute. Let me start with AIP 43 about DAG processor separation. This AIP is about separating the DAG processor process from Airflow scheduler and running it on a standalone host, different from scheduler job. As a result, the DAG processor can no longer affect scheduler work or vice versa, that we see now if Airflow is overloaded. And most of the work is already done. In Airflow 2.3, it is possible to run independent DAG processor. Even though the change looks simple, it requires some refactoring. For example, scheduler job and DAG processor exchanges information about callbacks through multi-process pipe. Callbacks are just some functions defined by the users, which should be executed on some conditions, for example, DAG or task failure. Of course, when scheduler and DAG processor are executed on different hosts, then multi-process pipe can be used. Instead, we decided to use the database as our queue for callbacks, with one component writing them to the new table and the other reading and executing. So in Airflow 2.3, we can run independent DAG processor. As a side effect, scheduler job, named Airflow scheduler in this picture, no longer needs to sync DAGs from the bucket, as it no longer operates on any user code. It means that this process fully meets the definition of trusted component. Of course, DAG processor separation is an opt-in feature. To use it, you need to configure your Airflow instance. Please see the AIP 43 for details. I mentioned that this AIP is almost ready. So the only remaining part is possibility to run multiple DAG processors, each parsing DAGs from different locations. This could be used either to separate the DAGs that are heavy or slow to parse from others, maybe production critical, or separate them by teams or developers. I can also imagine that in the future, each DAG processor may use different service account and set of PyPy dependencies. But please remember that workers are still shared, so some more work is needed here as well. Second AIP is about solving the direct access to the database. Again, if you need more details, please check the AIP 44. We can see on this picture the two components that are considered untrusted. So we have a DAG processor and Airflow workers. They execute the user code, but still have access to the database. And this is a dangerous habit we want to finally break with. The idea for this AIP is to introduce new component called internal API. It exposes a limited number of operations that can be executed on the database. And this is fully trusted component running only Airflow community code. DAG processor or worker can no longer connect to the database directly, but they can only make calls to this internal API. The requests are, of course, translated to the SQL query and executed on the database, but the code of this internal API is reviewed by Airflow community. And of course, the list of methods is strictly limited to only what is needed by worker to run. So dropping the table or database is no longer possible. There is still one problem with authorization. A particular task or DAG should be able to change only its own state and have limited access to secrets or connections. In the first phase, we plan to do simple check, whether the calls comes from the worker and probably with some long-living tokens. Later on, the community plans to introduce fine-grained access control, and there is a different group of folks working on that. The feature may bring some breaking changes. So for example, if user DAG or tasks depend on accessing the database, then they will no longer work. Due to that, enabling it requires changing the configuration. This AIP still needs some work. We have concept, we have ideas, but no code is merged yet. We just need to decide on some details to make sure the Airflow developer experience stays the same. And there is no need, for example, to implement the same features accessing the database twice, once in the normal mode with direct database access, and the second with database isolation mode. So these are two AIPs that Cloud Composer is working on right now. But what next? Let's look again on the architecture that I showed at the very beginning. The AIPs that I mentioned solves two problems. Airflow scheduler running two processes, untrusted DAG processor and trusted scheduler job. And second, direct access to the database for untrusted components like DAG processor or worker. DAG processor separation also partially solves the problem with a single DAG's location, as we are able to run multiple DAG processors pointing to different directory. However, DAGs from the same directory will still be parsed without any isolation of the same host. Moreover, tasks are still executed by the shared set of workers, so there is still some work needed here. What about other problems? Problem with workers running different tasks can be solved by using existing Kubernetes executor. It will create a dedicated Kubernetes pod for each task. And of course, for the cost of inter-task latency. Currently, in the community, there are some AIPs that could help there. There's an idea to introduce runtime isolation for tasks in a worker and DAGs in DAG processor by executing them in a dedicated Docker container. The image for the Docker can be defined at the task or DAG level, which actually solves the problem with PyPI packages configs, and user code executed in the same context as Airflow code. And of course, to make it fully secure, the fine-grained access control is needed to make sure worker and DAG processor can only access resources they need. We know that our journey just began, but we are looking forward to contribute in every single feature there as a single part of a bigger picture. And we are sure it will bring a lot of benefits, not only for our customers, but also for any users of our Airflow. That's all that I had for today. I hope you enjoy it. If you're interested in any of these topics, please check the AIPs that I mentioned. And remember that all of these activities take place in Airflow community. So if you would like to join and help, then you are more than welcome. Thank you.